Hey folks, this is the first semi-serious lecture that we're going to do that I'm going to put up on YouTube for you guys to watch. So let's go ahead and get started. We are still in the area of carbonyl chemistry. Well, now, remember, carbonyl chemistry looks like this. You've got the carbonyl group, and one of the things about it is it's got a built-in partial positive and partial negative section to the molecule. Probably the two most important pieces of this to remember are the fact that the carbonyl carbon there is partially positive, which means it is really good at undergoing a nucleophilic attack. Up here, you've got the lone pair of electrons on the oxygen that can do crazy little things like deprotonate something. Now, there are a variety of different types of carbonyl chemistry that you can do. For example, there's the nucleophile path, which you have the nucleophile attack the carbon, open it up, and your intermediate looks like that. The other option is the electrophilic or acid pathway, which the first step involves you protonating the carbonyl oxygen with an acid source, usually a hydronium, but we do have a couple more options that we can go with. What this does is it creates this charged carbonyl group right there. This is the primed pump, if you will remember, where you've already put your energy in, so the subsequent nucleophilic attacks should be reasonably easy to do. Pause. All right, so one thing that we really didn't talk about with this is when do you know whether or not you need to use the nucleophilic pathway or the electrophilic or acid pathway? And honestly, the answer to that comes from what is your nucleophile? Is it a strong nucleophile? Now, what are some examples of the strong nucleophiles? How about NaBH4, lithium aluminum hydride, Grignards, alkylithiums, and hydroxide and alkoxide ions. These are all your strong nucleophiles. These will prefer the nucleophile pathway. The reason for this is if you have anything remotely protic around at least this set, it's going to protonate your nucleophile instead of going after the carbonyl carbon, and you're kind of done. That's the reason that we had to keep the Grignard reactions and most of these so darn dry. Now, follow up to that is, when do you use the acid or electrophile pathway? That's when you've got moderate to weak nucleophiles, such as water or alcohols. Now remember, these form the hydrate and the acetal. Nitrogenous nucleophiles also tend to prefer the electrophilic or acid pathway. That's just kind of the way that they are set up. You got some options here, which is going to be in the next video. So before we go into that, though, I do want to discuss a small problem that we have with the amine. And that is, whenever you've got a free amine, or as we like to call it, a free base, meaning the nitrogen's got its lone pair of electrons, and you introduce this into an acid, what you'll regularly get is this, the protonated nitrogen or the quaternary ammonium salt. This can be problematic. So what we do is we tend to introduce the acids catalytically. That means very little of it. Usually 1 milliliter is considered massive overkill for something like this. All right, so one last page here to sum up real quick. Here's what's coming up for the rest of this unit. We've got nitrogen nucleophiles. Those are going to include, when you use a primary amine plus some kind of carbonyl in the presence of acid, you're going to get this. This is called an imine. If you use a secondary amine with a carbonyl in the presence of just a hint of acid, what you're going to generate looks like this. And this is called an enamine. So before we go merrily onward into the next video, this is I want to go back and just do a quick review of everything that we just talked about. Carbonyl chemistry typified by the C double bond O group there, partial positive on the carbon, partial negative on the oxygen. What that also does for you is it shows you the sites of reactions. 2 pathways that these can undergo. A direct nucleophilic attack, which involves a strong nucleophile attacking the carbon, breaking open the carbon-oxygen pi bond, forming a bond here between the carbon and the nucleophile, and a negative charge up there on the oxygen. The acid pathway tends to protonate your hydronium, be protonated by your hydronium. Then you get this positive charge here. Now this, again, is the phrase priming the pump because it makes this carbon much more reactive. Okay, so when do you know to use the nucleophile or electrophile acid pathway? If you've got a strong nucleophile, like the list we have here, then you're going to go with the straight nucleophile pathway. Mainly because if you bring an acid anywhere near these, you're kind of sunk, because they are far more likely to simply protonate these strong nucleophiles and therefore kind of not do any reaction at all. You use the acid or electrophile pathway with moderate to weak nucleophiles, such as water, alcohols, primary amines, and etc. These give you, wow, that really fell apart. Let me try that again. You need to use the acid or electrophile pathway when you have weak to moderate nucleophiles, like water, alcohol, and our friend the amine here. Now, the reason we're going to kind of focus on the amine is because that's what the next video is about. With the nitrogen nucleophiles and the amines, you've got 2 options. One is if you have a primary amine, a carbonyl, and an acid, you make an imine, which is typified by the C double bond N. If you make a secondary amine with that carbonyl, you've got with a little bit of acid, you make an enamine. So next time we're going to talk about how we make these two nitrogenous derivatives, and we'll look at mechanisms and uses. So see you then.